Good morning. The topic for today is about low power clock, interconnect and layout designs. The reference for this would be the book by Soutress, chapter 8, and the references what you will find at the end of the chapter. A lot of good materials are there in it. And in the digital design practices, what we had been having in the theory and the lab sessions throughout the first and second semester, the rules what we had been following inherently are the simplicity what are needed for the designs, and which would make, of course, the simplicity would make the regularity possible, and the regular structure would make the replication of the designs possible, and the designing of a very complex circuit would be easier. And smaller is faster. The rule 2 what we would have is smaller is faster. When you go for designing a particular application, for a particular application, you would always choose to be making the design to be compact, which would help in higher speed for the designs. And the third rule what we had been following is learn to compromise. While doing the designing, whatever be the parameter which is necessary for a certain application, go for choosing at the cost of something else which is not going to be so important. So whatever be the application, based on that, the good design will need some trade-offs between parameters, two parameters. The rule 4 would be make the common case work faster. Whatever be the common case which is going to be important, which is going to be at the heart of a system, make that work faster, and after that you have the other peripheral designs along with the main component to be working faster. For example, we would always, whenever we talk of a microprocessor or something, we would talk about the ALU, what you have got inside to work efficiently, and after designing the ALU, next would come the control unit, program counter and all, and then only you would go for the peripherals. The peripherals which would work for the speed what is necessary for your particular ALU. So the common case, if you concentrate efficiently, naturally you would go for getting a good and better designs. All these were discussed before. Before going for the topic on the clock, interconnect, the series, concentration what we have got to put into those, some recalling is needed. The first one is the clock tree. The clock tree, the simplest and the most efficient clock tree structure what we have studied. I may have the clock entering from a particular point. At this point, I have the clock generation made and entering here. From here, I go for dividing that into this shape. What you have is the H clock tree, and you have this clock entering here, this goes this way and that way, thereby it sees equal load, and here it goes one branch, another branch, and here another branch, second branch. This way you have equal load at any point. If I look at, you have equal loads. This is the use of your H clock tree, what is famously called as H. And you have all the other flip-flops, latches and all these timing elements to be supplied by whatever be the clock what I get out of it. So considering this to be the total chip area, I have the total chip area supplied by the clock for the timing elements. Okay, the next type, the more different clock architectures what you might have used also are what we have seen just now, the H clock tree, and then the next one would be the mesh structure, what I have as the clock source, and from the clock source how I am taking it over in a mesh like form to the different areas across the chip. The total chip area is here, and this total chip area is supplied with the clock from here around everywhere. And then I have another thing called hybrid. In this hybrid, I can have a mesh and I could have a local tree like structure, what we have seen already. And this is a tree structure along with cross links also, so that I would have balancing of clock path. All these are the efforts what people had been taking while designing the synchronous digital designs which would take care of the timing operation of a circuit. The timing is so important. And when we have the timing to be considered, the major thing what we would arrive at is the clock, which is the heart of a circuit, heart of a chip, I could say. From the clock source only, I will have all these things entering the various areas of the chip. And the clock's Q, the parameter what we would now go for introducing, is a very important parameter. Clock's Q and jitter we have studied already. For example, in the figure what we have taken, I have my original clock entering at this point, and the flip-flops what are supplied by this particular arm of the edge would be having their signals traveling all the way here up to this point. Whereas if I go for taking this particular thing, I have here division, and for this particular thing I have this. What I have in this particular arrangement is that each and every path whatever I am taking for the clock, I ultimately realize equal time at which the particular flip-flop is supplied by the clock. I would want to have the clock signal travel through equal paths whatever be the clock elements are. We try to manage and we get the H clock tree in this manner. But we cannot expect to have a uniform structure with distributed flip-flops, and flip-flops are timing elements of the same density in each and every point. I may have a total chip, and within this chip I may have my digital parts here, I may have some peripherals here, I may have some other controller controlling here, and I may have some interfacing here, some communication interface here. All these would go for working with the clock, and from one particular clock source I will ultimately go for making the clock signal travel everywhere. And as you can see, not all the particular modules are going to be supplied by the clock at the same time. You will have the clock signals reaching each and every point at different timings, and this is the main reason why we have the clock's Q. When I talk of clock's Q, I may have a particular clock signal, and this at a particular point of the chip may enter so delayed, and it may enter some other point at this time. I would now have the time difference what I have here to be playing a major role as the clock's Q. This is what this spatial incoherence, spatial disturbance, depending on where the clock is originated and how long it has traveled, this distance is going to be mattering. And these Q are going to be so serious a thing in our any digital system design. The microprocessors what we have are naturally supplied by or clocked by a common or a global clock signal. We call it as global because it's going to be taking everywhere across. And the maximum, the largest difficulty is to have, we need high frequency everywhere, and high frequency global clock of the order of even gigahertz range now. So when I talk of gigahertz range, multi-gigahertz range signal, if I want to have a 1 gigahertz, I should have twice that 2 gigahertz to be generated. Maybe I will go for dividing this by 2 and go for supplying after shaping. Of course, after shaping that clock signal, I am sending it to the chip. And this high frequency signal, when it goes through different paths and different lengths of wires and different types of loads at its ends, would now be acting very, very differently. So my operation, my main concern would be to let all the clock signals whatever I have, reach all the timing elements like flip-flops, latches at the same time. I should now go for identifying which particular path is receiving the clock early, which is getting the clock late, and based on them I have got to be, if needed, wire snaking. I would make the clock to travel through a unnecessarily larger path just to manage the equal skew at the particular points which are under consideration. And in some cases, I would go for adjusting even the buffers. I may want to have the clock from here reaching a longer path there, and there may be a very shorter, a smaller path what I have. So here I have got a unit 1 and here I have got a unit 1 and 2, and I will have these two supplied by the same clock source without any skew. In such a case, what I would do is, at this point I would add more of buffers, and this would give sufficient energy, sufficient push for this clock signal to reach it early, so that by the time this signal reaches, the clock signal also would have reached unit 1. So unit 1 and unit 2 would now be working in order. That means I will be introducing these sort of buffers on the way in the path of the clock itself. So these sort of balancing using the buffers are possible. And the number of crossovers from one area to the other, all these are different tricks by which we would adjust the clock skew. And these solutions, what I am doing, unnecessarily introducing wires and redundant number of buffers, all these and the crossovers, all these are going to be the overheads, the extra materials, extra circuit what we introduce, and these lead to power consumption. Imagine how much of power actually we are spending in the clock circuitry. A typical set of processors we have taken in the book, also the same example, though it is of 10 years old, it will give you the necessary idea. Anyway, it is for the DCE Alpha 21164 processor from Digital Equipment Corporation, and the clock drivers what they have used, the structure, that's what you are seeing now. In the left, what you see, they are your clock buffers, and these clock buffers drive the wires and the clock signal reaches this point. And I may have the first part. I have the first stage of the flip-flop, and the next flip-flop I have, between which I have got some logic, and I will have some sequential element also, some feedback element. This logic I have got, and this particular circuit, looking at it, you have something here now to see. We said this is a very long wire. Clock is generated somewhere here, and from here to cross the long length of wire, with respect to the RC, you have seen RC modeling and all you have studied, you calculate and you find out what is going to be the total delay what is incurred in this. And that delay, if I find out, it seems it is around 90 picoseconds. What was there measured in DCE Alpha, the processor. So what will the digital designers do? They had gone for having the logic, that transition delay through that logic, they saw to it that it is more than whatever be the delay here. That is what they had practically done. I hope you follow what I am meaning to say. My job so far had been to design for the functionality. Logic design. I wanted logic design for a particular functionality. That is what my concern was. Now what has happened? A logic I have got, and I have a long path for the clock to go, and the clock signal is supposedly traveling a long distance, and it comes across so much of skew, and because of that skew, in addition to the functionality what I would normally be bothered about, I have to now bother about this skew also, so that my transition, my delay through this logic path happens to be more than what I will incur in this particular path. That is the situation. That was the situation even some 10 years earlier. Now you imagine with our UDSM technologies. That is because previously we were all working with the micrometer devices. When we were having micrometer devices, this was big enough, and all the nodal capacitances what we had been studying, they were all of appreciably higher values, and you had such devices to be connected by so many interconnects and all. Nowadays what has happened, the devices have shrunk and the interconnect wires have gone increasing. This is the problem what we had been many times talking about also. And this particular example what we have taken for you is, I have the wire and I took consideration that my logic is going to be having more delay than what I will have as the skew, but even there I have taken some other additional step also. What is that? I have so many buffers driving this length of wire, and you know how much of capacitance we have at this node point, that is around 3.75 nanofarad. And imagine this particular capacitance and operating at a certain voltage, how much of power would it be dissipating? That 12 watts power dissipation. That means what? We were in the original some 10 to 15 years back, we were talking about only the CV square F only for the capacitance of the nodes pertaining to the logic. Nowadays you have the clock power itself to be even equal to 50% or even more than 50%. This is what is the reality what we have now. When we have such a case, how to effectively go for tackling? We need to have the clock for keeping the complete system working in synchronism. But at the same time, we have the clock to be eating so much of power. So how to effectively control them? This is what is our discussion also about. And there is another example what we have as the Itanium microprocessor, in that we have a common PLL which generates the main clock, and maybe it will have 2 GHz generated, and I would wave shape it and get 1 GHz output from that, and this 1 GHz is passed through the total clock. And what they have done is the same original clock, they give it as reference clock and they pass it through. These things are going through the drivers, and this goes through a straight simpler path, and what you see here are the de-skewing clusters. And the de-skewing clusters would take the reference clock here, which has incurred only very small amount of delay here, and the clock what had been traveling through all the paths which had been supplying also, and which is reaching the particular de-skewing cluster maybe after a certain delay. And the de-skewing cluster would now go for comparing these two. Our aim is to do what? I have the total circuit with these grid structures. These are the parts, component areas of the chip, and I would want to have all these to be supplied by the same clock without any skew in between. That is area, this square one and another square here are to be supplied by the same clock. So what we do, we receive the reference and the delayed clock, and we de-skew, that is with reference to this we are making this work, and then we are supplying it to the grids whatever we have here. This is what is the arrangement what they had done there in the Itanium microprocessor. And these type of circuit arrangements we have at the cost of redundancy. The de-skewing clusters, all these are redundant, but without that we cannot actually live without that anyway. And the reduction of the clock power, how can it be achieved? What are the general ways and means? We were just talking about the clock, how we supply, and what are the ways in which we distribute the clock, and in practical cases how much of clock power is actually dissipated, and all that we saw. We would always not want to introduce any extra things like wire snaking, extra buffers of in the previous figure what I had shown you. You had this W, what contributed for all these buffers was 58 centimeter. Imagine, it is using some 180 nanometer device what we had, and using 180 nanometer device they had gone for a total of 58 centimeter width of devices. Imagine how much of chip area it would take and how much of power dissipation would be incurred in that. That is a thing. And so we go for having hierarchical clock tree, and the hierarchical clock tree to the extent possible we would want to have both the arms to be having the same clock load, and the same amount of skew we felt would be there using your H and all what we had been discussing in the previous slides. And careful design of the clock drivers, that would be the next thing. What is this for? The short circuit current what we will have when I go for having the clock drivers. Naturally, whatever be the inverter I have, there should not be any short circuit, and this itself should not be consuming the power. And we would ultimately want to have, when I consider this H clock tree, here I am having some load and here I am having some load, I say that, and all these loads are actually what? The flip-flops and the latches, and as far as possible try to reduce the flip-flops and the latches, the timing elements. And even if I have got one flip-flop, see to it that minimum number of gates are driven by the particular clock signal, minimum number of gates of transistors, individual switches to be operated by the clock. We have got to see to that. Then next thing would be, whenever I have a particular requirement for a certain application to be operated at maybe 1 gigahertz, I would want to have 1 gigahertz minimum frequency, and I would want to have to reduce the clock power and to increase the efficiency. I may think of something like, during the positive edge I can get my circuit working, during the negative edge also I could get my circuit working. This is what is the double edge triggered flip-flops, what we have studied maybe in the last semester itself, but which will have some other sort of problems what we will see. Or we can have even parallel logic modules, logic at the cost of logic redundancy. That is what, this is what is the trade-off. I may want to have a certain set of operations done at 2f frequency, or otherwise what I can do, I can have two such blocks. This is one particular block, this can be replicated by two blocks, and I can get both of these operated at FF frequencies. Ultimately I would have the complete work anyway done with. But the thing is, I would want to have parallelized redundant logic resources I would need. Otherwise what we do, multi-rate clocking. My ultimate aim is to reduce the clock power. To reduce the clock power, what I can now do, whichever particular module is to be operated at F, whichever module is to be operated at, I can afford to operate it at half of the frequency, or I could operate at 1/4 of the frequency. All these I could identify and use a multi-rate clock. I need to have only some dividers to have F by 2 and another divider to go for F by 4 and all that. And the moment I work with so much of reduced frequency, naturally my power dissipation by the clock is going to be proportionately reduced. This is the thing what we would be following also. The clock power, it is a dramatic problem. That is why this lengthy discussion here. Why the clock power can be as large as logic power, and as I told, it is not only 25%, it could even be nearly 50% even with the current day technologies. And the clock power self-timed. They are actually timing clocks, what we have here. If we don't want to have the clock dissipation, what I can do? I have one unit. The moment the data from this is ready, I could get my second one operating just by the use of the data identifying whether it is ready or not. That is using sort of handshaking signals, what we have discussed before. Handshaking signals. And they are self-timed and asynchronous techniques. We call them asynchronous or asynchronous, and these asynchronous techniques help in not using any particular clock at all. That is one way of avoiding the power dissipation. The next one would be a very good point. What we are really actually following is in SoC, system on chip design, we go for globally asynchronous and locally synchronous. What is our actually problem? My area of chip is very long and I have one clock generated here. The reason why I need to travel all the way to reach all those places make me suffer from the particular skew and all that. So why to bother about? Let it be globally asynchronous. Each of the different units, let them work at various frequencies within their own modules, and within their modules let them be synchronous, operated by a certain clock. Globally let it be asynchronous. That is what is another solution to avoid this problem of clock. And in that way, if we look at, there is another such option also. Each chip would now be having different regions, first region, second region, third region, fourth region. Each of these would be now operating at F1, F2, F3. I hope you remember we have discussed sometime about different frequency and different voltage ranges also. I could have this operating at V4, V5, V6. So the first unit would be operating at V1, F1, V2, F2, V3, F3. So you will have multi-voltage operation and multi-frequency also. This would efficiently, naturally, based on the particular job, what is there interested with each of these blocks, we would now be identifying different power dissipation for each of this. So whichever is the very important part, go for working at a very high frequency. The remaining thing, you go for working at lower frequency. And similarly so with, if I need a very high speed performance, go for working at higher voltage. If the speed is not so important, I would want only the power to be the main factor which I am concerned about, then go for working with lower voltage. This is what is the trading of what we had discussed even at the starting. And another way would be to make, I have my chip around everywhere, use PLLs, and these PLLs would now go for taking their reference clocks and use phase detectors, and those phase detectors would identify the particular clock, the main clock signal, and based on that they would go for deciding about, they would go for generating the clock locally and send it through the clock tree for distribution to all the chip areas. That is the another thing what we normally do nowadays for tackling the clock power problem. The next thing what we had been talking about, the clock distribution and all that. We talked about even two cases of two processors, how they are actually tackling the issue. The next would be what we have as the clocking scheme. We were so far thinking that the flip-flops, which are edge sensitive, are the timing elements. And using these timing elements, we were working with all the circuits operated. we had so many advantages of this master slave flip-flop structure. The master would be operated by the phi 1 when it would be going positive, and when this goes negative, this would no more be responding to the signal whatever I have here. Instead, the phi 2, whatever be the output was at this point, would take it up and it would go for working. That is what we had been studying as the master slave flip-flop. And the master slave flip-flop frequency, this is what the on time I have, off time I have from this figure itself. The on time I have, the off time I have. The phi 1 I would have this working, and then I would have the next time I have got this. We continue with the latch based clocking scheme. The timing elements, flip-flop versus latches. That is what we would see in this figure. The first one says the master, the next one would be the slave operated by the phi 1 and the phi 2. All this we have dealt with earlier. We will say that this is not very robust. Why they are not robust? In the case of a latch, they are going to be level triggered. We have seen that. And I have the latches operated by non-overlapping power clocks as we have shown here, phi 1, phi 2 and phi 1 and phi 2, and because of the non-overlapping clock phases what I have here, I always have this extra time between. This is going to be help me tackling the problems. How it is, we will see here. How the time borrowing concept happens. In the case of a flip-flop, I have one clock edge coming, and by skew another clock dash what I have, and the unit is expected to work because of the skew. Despite the Q, it has to get on by this positive edge. There is no other go for the circuit. So the computation time is reduced now by this much of amount. So whatever be the frequency at which I had been expecting my circuit to operate, if the logic is going to be taking more time, then the logic cannot be functionally correct, and then I will have to rework on the logic and the frequency. This is what I will have to do if I go for flip-flop based design. The same case, if I go for latch based design, what will I do? I have the original clock or my skewed clock. I would be able to get, as long as this level is on, my data could enter, and I would have my computation time to be extended from this point to that point. Because of the skew, I am not going to be having reduced computation time at all. Rather, I am able to borrow extra time for this. This is called as time borrowing. We see the same figure with more comparison between flip-flop based and latch based here. As you see, the clock, what I have operating, if the clock had come in time. But because of the skewed clock, I have this coming early, and as I showed in the previous figure itself, my computation time as related to the flip-flop, D flip-flop with the master and slave structure, I have only this much of time. But given with the latch arrangement, I have one particular latch operating with one phi and the other phi. Till such a point is reached, I have the computation time possible, and this difference what I have here is called the time borrowing, what I mentioned in the previous slide. A better example what I have with some numbers is, I have one particular logic level and I have got phi 1 the latch, followed by logic 2, another phi 2, logic 3, phi 3, logic 4 and phi 4. And how my time borrowing is going to be effective. Let us take, I have a certain logic what I have here, that path 1, it may be taking 8 nanoseconds to complete. So what I do, my time is from here to here, only 5 nanosecond. Whereas because of the facility what I have here as the latch, I may go for designing borrowing time into even the phi 2. The time of 3 nanosecond I could borrow. So my computation for my logic L1 can start and it can extend further beyond the 5 nanosecond time what I have here, and it may go into 8 nanosecond totally, and this is the borrowed time from the next clock duration. And for the next operation I need to have only 2 nanosecond. So there is no problem when it is on. I would have that operation also getting completed. So my first job is done and my next job also is done. And for the next thing I want to have 6 nanosecond. So I will start from here. For the 6 nanosecond for the path 3 it would go with this 5, and along with 1 nanosecond borrowed from here I could take, and with the use of the 6 nanosecond what I have realized from here to here, with the 5 nanosecond here and 1 nanosecond borrowed from this point, totally 6 nanosecond I am able to complete this job also. And then I have my path 4 with the 2 nanosecond duration that I will be easily able to complete with from the next 4 nanosecond what I have. This is what is the advantage what we have out of the latch based design. I could go for borrowing from the next or from the previous, and I could design all these logics in such a way that I am able to get my full functionality for the logics accomplished within the total times, and I would be able to have my frequency of operation to be maximally whatever is possible useful. And this way it will not be possible for the same flip-flop based circuit, because in the case of flip-flop based circuit, given with the maximum time of 8 nanosecond, I should have gone for all these stages 8 nanoseconds duration only. Whereas I would need only 2 nanosecond, 6 nanosecond, 2 nanosecond, unnecessarily I would be spending time, and I would be introducing delays to calculate, because the maximum delay whatever I would have through one particular logic path would determine the minimum, that is the frequency what I would operate for the flip-flop. So that would limit. This is the advantage what we have out of the latch based clock gating. So normally how we go about deciding the latch based clock gating is by using this. We can even go for clock gating. Another terminology what we introduce is the clock gating, to reduce the power and to effectively operate. We said within this time it's going to be operating, and after this time for 6 nanoseconds it would be operating, for 2 nanoseconds it would be operating. All these, how are they going to be possible is by gating and sending the signals. Here I would have the latch based clock gating. I would have my first latch and a combinational logic circuit. What I have shown the previous figure, I have shown it in some other manner only to show that I am going to be gating as required for my particular application and send it. But only thing what we have got to remember in the case of this clock gating thing is, I would have these gates. If it is an AND gate, naturally it would be an AND gate followed by one inverter, and this particular gate should not be taken by the tool, for example Synopsys, as a gate component which is to be optimized also. So we have got to put, it shouldn't be optimized. This you introduce it just for the purpose of clock gating and timing the sequence of data flow. So this shouldn't be left for optimization by the tool. If we do it so, there may be, the tool may think of like how it does the optimization for the combinational circuit. It would take this also as another part, and it would go for placing this combinational in between, or this may be taken this way. Nothing should happen like that. So when we go for designing such things in the EDA tools, we would have to give a don't touch attribute for this particular thing. Normally we call it as a don't touch attribute, and using them we go for working the timing between each and every combinational logic functions for the latch based clock gating. The next topic, major topic, what we would go for having is the interconnect delays. Before going for interconnect delays, we have got to talk about something else also. Previously, we were all working with micrometer size devices, and then we went for deep submicron, what we called. In the case of deep submicron, we went for nanometer devices, and we now call ultra deep submicron where very few nanometer. Here when I say hundreds of nanometers, it is going to be even maybe around 10 nanometer, 11 nanometer, 15 nanometer device, 22 nanometer device. All these now we are working, whether it is a FinFET or any other IGFET devices, it is going to be of such a order that we are working. Now, coming to the devices, how the scaling, the effects of scaling have got to be discussed now. It is important before going for the delay of wire. When we consider the delay of wire, we were having our devices scaled as W for the width of the device, L for the length of the device, and maybe the thickness for the oxide thickness mentioned as a D. Now, when we went for scaling, we always went for reduced size that we called by W by S, and the length would be L by S, and this also would be D by S. Because of this, what happened to the substrate doping, the N substrate or P substrate doping, how actually it got affected? Because the feature sizes got reduced, we would not want the strength of the strength of current to reduce. So we would want to have within a very small feature space, we would want to have more charge carriers. Therefore, this would now be scaled by multiplied by S. Whereas we called here divided by S, it's going to be multiplied by S. And similarly, when I would want to have the VDD, VTH and all considered, how are they going to be? When I am having my W, L, D and all reduced, I cannot afford to have the same VDD of 5 volts as I did for the 2 micron device given across a nanometer size device. So I will have to accordingly reduce the VDD and VTH also. So that also, let us assume we are having the VDD divided by S and VTH also divided by S. Now in this case, what happens to the current IDS? What happens to IDS? IDS, as you normally know, half of beta VGS minus VT the whole square I put. What happens to VGS and VT? You know, we have discussed here, that is having 1 by S, this one. And for beta, beta is what? Beta is determined by half of your device transconductance. So before that, half of mu, your mobility, and your permittivity divided by D. This factor is giving you the process transconductance, multiplied by W by L give you the total thing as the device transconductance. This multiplied by your VGS minus VT the whole square. That's what our this one is. Now what happens to mu? It's not going to be scaled, neither permittivity is going to be scaled, whereas D is going to be scaled as D by S, and this as W by S, and this as L by S, whereas this is going to be 1 by S the whole square. That is what is going to be. So ultimately my current is going to be 1 by S in times IDS. I have only one S remaining, and here one S goes from here. Therefore 1 by S IDS. This 1 by S IDS is going to be the current what I have for the scaled technologies. Another thing what I would have is what will happen to the gate capacitance CD. I would call this as gate capacitance CG. What would happen to CG? Naturally, this is going to be determined by the permittivity divided by the D I into W into L, and permittivity is not going to be changing. This is going to be changing, and this 1 by S into 1 by S divided by 1 by S. So this is going to be ultimately 1 by S also. And how about the mass resistance? Mass resistance, what we have, whether it is for the diffusion or metal wire or whatever it is, we normally call this mass resistance by the resistance what is there for a square unit of length. Therefore, this is not going to be changing. Whether it is a smaller square or the bigger square, it's going to be the same, and this is not going to be changing, so we would call it as 1 only. And then the next one is going to be the gate delay. When we talk of gate delay is going to be your TD, what I would mention, C times VDD divided by IDS. So this is now going to be how C is changing, 1 by S, and how VDD is changing, 1 by S divided by 1 by S, by which IDS is changing also. So ultimately this also is going to be 1 by S only. And next component what I will deal with is the power. The power is going to be what? I into VDD. Therefore, this is going to be 1 by S into 1 by S. So supposedly we are having an advantage of the power reducing by 1 by S square. And the density, what happens to the circuit density? Previously we were having a certain size, and now we are going to be reducing. So as the size reduces, naturally by the amount of scaling, I would have the number of chips also going to be increasing. So I would simply put it as S square. With all this, we can feel happy that we are having more density and reduced power reduction and all that. But in practice, is it happening? So when it comes to the interconnects, we were very happy that our devices got smaller, and we had power to be smaller and the voltage also less. What happens to interconnect, we will see from this. This is the case when we had our before scaling. We will have capital W is the width, the length of wire, height of wire, and the distance what determines the capacitance, and the delay in this case what it is we will calculate. And this is the current day device, the interconnects what we are using with the current day chips what we have. What we now have, the same L we maintain, because we are actually reducing the device sizes, we are not making the chip wafer to be reducing also. Previously we were all working with some 200 mm devices, 200 mm wafer, and then we went for 300 nanometer wafer, and now we realize 350 nanometer devices very coolly, 350 nanometer wafer devices we are going, and within that 350 nanometer device we go for taking all the number of components, whatever chips possible we are able to get, and this is the integration advantage what we have. And this we are trying to even take it to 40 centimeter, and that we are doing 40 and 45 centimeters we are trying in the recent foundries. Therefore, what happens ultimately is, even if we go for reducing the device sizes, we are not actually reducing the length of the wire at all. So the length remains the same, because we have more compact devices placed and more complex circuits involved in the integrated circuit. Naturally we would have large amount of interconnects, and as you know, even within one particular 1 centimeter, I read somewhere you have around 4 kilometers to 5 kilometers of wire inside the interconnect length. With such a case happening, naturally I would go for scaling W, I would go for scaling H, scaling the D, as I normally do for the other cases, whereas I know my L only is remaining constant. So W is W by S, D is D by S, and therefore the delay is going to be C dash R dash is going to be into S square because of the factor S, the delay. Okay, RC, the RC time constant. And similarly, if I compare the resistance for this case, what is it going to be? This is L. So L times, I have this L times the unit resistance, and this is going to be inversely proportional to W and H. And W, if it is more, I would have W and H, the cross-sectional area. If I have more, naturally my resistance would be less, and if this is less, my resistance is going to be more. The normal formula what we have. And now as you see here, W is scaled as W by S. That is, W is nothing but W by S, H is nothing but H by S, and this gives you the resistance increasing by S square. Though we use the same material, we are not having the resistance to be the same. The unit resistance is not actually remaining the same. It goes for increasing. To tell you particularly, previously for a 500 nanometer technology, we were having for 1 millimeter wire a 94 ohms of resistance value. The same way, if I consider a 100 nanometer technology, the value is around 140 ohms. Compare this. So if I go for technology nodes less than 100 nanometer, it is still going to be worse. And how is going to be the capacitance varying? The capacitance is nothing but your W times L divided by T. What capacitance I am going to be having across, and this capacitance, once again we will go for calculating. The W is going to be W by S, this W, L remains the same, D is going to be D by S, and therefore we have the capacitance remaining the same. The resistance is increased by S square, capacitance remains the same, and therefore the time constant what I would have in comparison with the previous case would be S square times RC. Now we have a problem. We have the devices conducting at a particular speed, whereas the interconnect, the delays increasing. Whatever be the scaling what we are attempting, the delay is increased by S square, and this makes it important to go for dealing with ways to tackle the interconnect delays. One such a way, not only one, the practical ways by which we have started working for reducing the gate delay is by the use of, from this itself, by the use of the material what I have here, or by adjusting the D, that is by suitably changing the gate oxide types what we have as the insulator. All these have led to this particular graph is the product of one particular research what they had accomplished. Then the use of aluminium wire, the use of copper wire, and using them individually, how the total delay of aluminium and copper are there. As we had seen, as we have discussed, the gate delay for the aluminium, how the gate delay as the technology shrinks is this curve what you see for the aluminium wire delays, and copper wire delays is this much only, and the total delay of copper is this much, and I have aluminium wire delays to be, as I showed you already, the gate delays are going to be this. When I was working with a larger device, the gate delay was more. As I shrink down, I have my gate delays to be coming low. Agreed, it's an advantage. But when I go for comparing aluminium, when I worked with 0.65 nanometer, the aluminium wire delay was less, and when I worked with the latest technologies, the 100 nanometer, I had my wire delays to be increasing. So the total delay is going to be the sum of gate delay plus aluminium wire delay, and that is what you see by this graph. The same way, if we can have the copper replacing, we have replaced the copper, that is the aluminium with the copper. When we use copper, how it is operating? This happens to be the gate delay, this happens to be the copper wire delay, and the copper gate delay and the total delay together we are drawing, and this is what it is. And this will tell you that for each and every type of the particular foundry, here I am showing you 0.25, 180 nanometer, 130 nanometer, 100 nanometer. At this point of time, whether it is aluminium wire or copper wire, I have a knee, that is the point at which I have my minimum most possible delays, taking into account both the gate and interconnects into account possible. Whereas for this point it is this way, for aluminium wire it is around 350 nanometer. This is what is the work what had been produced. This actually is to depict the effect of introducing good conducting copper wire in place of aluminium wire. If we would still want to reduce the wire delay, even some more better conductors like gold, silver, they could be used, but all the same, how the contamination of the oxides, how you have the foundry process going on, all these will determine the feasibility of such an attempt. And as we have discussed, the gate delays and interconnect delays are so important, and for each of these two metals, aluminium and copper, we discussed. And this is about the interconnect wires, how the interconnect wires, we have seen the chip has grown in complexity, the complexity is more, and we talk of billions of transistors inside one particular chip, and we even talk of system on chip which will have the complete thing here, and because of that naturally the devices so high in numbers would need so many interconnections also, and so many interconnect wires also we would have. And this picture is what you are seeing for that. This is metal 5 and 6, and this is metal 4, 3 and 2, 1, all these metal wires. As you see, the bottommost metal, how thin it is, the next bottommost metal 1 and 2, metal 3 and 4, its cross section, how you are seeing here, and metal 5 and 6, how big they are going to be, you are seeing here. Metal 7, 8, 9, 10, for recent processes even 11 metal wires are there. And as you see, because this wire is placed so much away from the substrate, naturally the D is so long, and you can afford to have very wide wires to have your resistance to be less, and the capacitance is not going to be unnecessarily increasing also because of this distance. Whereas here I would want to have the capacitance to be less because the distance is so small, so I would have my number of wires also, the capacitance is less, and the resistance also at this point of time you have given by this much of a width. That's what we normally do, because if we have so much of thick wire, naturally I would end up with more capacitance. Resistance, if I would want to reduce, I have got to have my metal width to be very big. But if I go for a very big metal width, naturally I would go for increased C. So in the process of reducing R, I am increasing C. So this is not acceptable. Therefore we go for limiting ourselves with a certain width for the metal 1, 2 and metal 3, 4. Whereas here, because I am having so much away from the substrate is so much away from this, here it is no problem at all. And a typical view, what you have got to see, the metal lines in 4 metal layer process, what you see from here, that is the topmost metal, the vias what you see, the vias what you see, under that you have the chip, and to look at it nicely, Here it is it's a microscopic view. It's an expanded, a magnified view what you have. This is the actual chip. Whereas above here to the whole length you have the interconnects. So the maximum area, the volume of any chip is only the interconnects. So imagine what it would be if we realize a 18 layer metal wire, and how much of complex ICs would be here inside, and how much of crosstalk play between victim and aggressors are going to be taking place. And this is what is about the crosstalk. That is when we talked about the metal wires, it is a cross section. I have my metal wire running like this, and these faces what I have here and this face, they face each other, and from this layer to the substrate naturally I have a capacitance, and because this is very far off I said this is not so serious, I said, but these things are serious. Why I make this to be so taller? Because I would want to have my cross section to be high enough to bring down the R resistance, and this process ultimately creates so much of side wall capacitances and area capacitances. These are the things what have got to be tackled also, and these are the research issues what we have with us when we go for interconnect theory. Now we talked about crosstalk. In the previous figure I said you have a capacitance here, and all these capacitors are getting only more as the technology goes down. We said then what would happen because of these wires? Imagine I am going from here from a 0 to 1, whereas this is at 0. This 0 to 1 race on one side of the plate naturally would go for taking a toll here. So if it was going from 0 to 1, or it was going from 0 to 1 or 1 to 0, naturally this is going to be affected by this. This is why I call this as an aggressor and this as a victim wire. And this could be a victim, and this could be affected by aggressor on the left side, aggressor on the right side also. If both are going in opposite direction, no problem, and if both are going in the same direction, this is going to be a real victim. All these are called your crosstalk effects, and because of this crosstalk, so much of concentration into the spacing of metal wires, the drivers, repeaters, what go into the design are very importantly being dealt with. Now the normal ways followed to reduce the crosstalk are very large drivers and repeaters to be less sensitive to aggressor node. Because even if there happens to be any strong switching action there, I should have my circuit flexible enough. That is, it should tolerate. Next one would be the metal wires are to be spaced in such a manner that they don't run parallel for long distance. Only because I have these two wires running in parallel that I get this. That is the reason why normally what we follow is, if I have one particular metal layer going horizontally above this silicon dioxide, I would have the next wire running vertical to that, and then the next layer running once again horizontal. That is, for example, this is Mi, this is Mi plus 1, this is Mi plus 2. That way we normally arrange so that we avoid the total amount of cross sections. And you can make use of the routers to take note of routing to reduce the crosstalk also. We should go for the EDA tools. Even while using the EDA tools, the crosstalk, the optimization with respect to the clock laying, we need to bother about. And the next one would be intra-metal dielectric with a low K to reduce the capacitance, that we can go for. And copper metal lines which could reduce your R, thereby I could go for reducing my RC delay itself. And the larger metal lines I could go for, but this larger metal line shouldn't increase the ground capacitance that we have discussed, but it could decrease the relative coupling capacitance, larger metal lines, and to work at a low VDD to reduce aggression. because only if you have a 0 to a sufficiently high voltage jump that the other one would be victimized. Otherwise, if I go for reducing this VDD, naturally the effect is going to be less. These are some of the ways, and a MOS transistor, a picture, how the connections are being taken out. The same picture, the layout design. These layout designs are what we will discuss in the next class, because whenever we draw one particular line like this, we don't get the same line in practice after the foundry produces a chip. You have this disturbed lines only. And what is the ways and means by which the layout design would be dealt with in the next session.